Somewhere in the constellation of Orion, a star is dying right now, and you will never know the exact moment it happened until the light finally reaches your eyes. Because what you are about to learn tonight will change the way you look at the night sky forever. Every single night when you glance up and find the hunter in the sky, your eyes land on a reddish point of light sitting on his shoulder. That star is called Betelgeuse, and it is not behaving like an ordinary star. It is a red supergiant, one of the largest stars ever observed, so massive that if you dropped it into the center of our solar system, its outer edge would swallow Mercury, Venus, Earth, Mars, and stretch out somewhere close to Jupiter. It is nearing the end of its life, and unlike our Sun, which will fade away slowly over billions of years, Betelgeuse is going to die in one of the most violent events the universe can produce. It is going to explode as a supernova. The question that keeps astronomers, sky watchers, and curious minds like yours up at night is simple. What happens to us here on Earth when that explosion finally happens? Tonight we are going to walk through this scenario step by step, using real physics, real astronomy, and real historical precedent, not science fiction. We are going to talk about what a star death actually looks like from 640 light years away, what danger, if any, it poses to life on our planet, how bright the explosion would appear in our sky, and why some of the greatest astronomers on the planet have been watching this star with growing fascination for the last several years. By the end of this video, you will understand exactly what would happen if Betelgeuse exploded tonight, and why the answer might surprise you. Let's start with the basics, because to understand an ending, you first have to understand what you are watching end. Betelgeuse sits at a distance of roughly 640 light years from Earth. That number alone tells you something important before we even get into the explosion itself. Light years are not units of time. They are units of distance, but they carry time within them. When you look at Betelgeuse tonight, you are not seeing the star as it exists in this present moment. You are seeing light that left its surface 640 years ago, back when medieval kingdoms were still being ruled by monarchs we now only read about in history books. In other words, Betelgeuse could have already exploded. It could have died decades ago, or even centuries ago, and we would have absolutely no way of knowing until the light and energy from that explosion physically crosses the gulf of space and arrives here. This is one of the strangest and most humbling truths about astronomy. The night sky is not a live broadcast. It is an ancient photograph, layered with light from different moments in time, some of it from stars that no longer exist. Now, why is Betelgeuse considered a strong candidate for an imminent explosion, at least on a cosmic time scale? The star is what astronomers classify as a red supergiant, and it is nearing the final stage of stellar evolution for stars of its size. Stars generate energy by fusing lighter elements into heavier ones in their cores, starting with hydrogen fusing into helium. Our Sun is doing this right now, and it has billions of years of fuel left because it is a relatively small, stable star. Betelgeuse, however, is a giant, roughly 700 times the radius of the Sun, and somewhere between 15 and 20 times its mass. Massive stars burn through their fuel at an incredibly fast rate. Where the Sun will spend about 10 billion years fusing hydrogen, a star the size of Betelgeuse burns through that same stage in a matter of millions of years. And once it exhausts hydrogen, it begins fusing helium, then carbon, then neon, then oxygen, then silicon, each stage happening faster than the last, like a car speeding toward a wall with less and less time between each mile marker. The final stage, silicon fusing into iron, can take place in less than a single day. Iron is the point of no return, because fusing iron does not release energy, it consumes it. Once a massive star builds an iron core, the core can no longer support itself against the crushing weight of the star above it, and it collapses in on itself in a fraction of a second. That collapse triggers a shockwave that rips through the outer layers of the star and blows them off into space in an explosion, so bright it can outshine an entire galaxy for a few weeks. This is a core collapse supernova, And this is the type of death Betelgeuse is expected to experience. So the science tells us Betelgeuse is going to explode. The real question everyone wants answered is timing, and here astronomers have to be honest about uncertainty. In cosmic terms, Betelgeuse could explode within the next 100,000 years, and that range might sound frustratingly vague. But on the scale of stellar lifetimes measured in millions of years, 100,000 years is essentially tomorrow. Some researchers studying the star's internal structure and pulsation patterns have suggested it could happen within the next few thousand years. Others argue it could even be sooner. And there is no way to pinpoint an exact date because we cannot see directly into the star's core. What we can do is watch the surface for clues, and that is exactly what happened in the winter of 2019 into 2020, when Betelgeuse did something that made headlines around the world. The star dimmed, not by a small amount but dramatically, dropping to roughly a third of its normal brightness, the dimmest it had appeared in over a century of recorded observations. Social media lit up with speculation that this was it, that Betelgeuse was finally about to go supernova, and news outlets ran breathless headlines asking whether the end was near. Astronomers pointed powerful telescopes at the star, trying to determine if this was truly a pre-supernova signal or something else entirely. What they eventually discovered was fascinating in its own right, even if it disappointed anyone hoping for an explosion. The dimming appears to have been caused by the star ejecting a massive cloud of hot gas from its surface, gas that then cooled and condensed into dust as it moved away from the star. That dust cloud partially blocked our view of Betelgeuse's light, creating what researchers nicknamed the Great Dimming. It was not the death of the star, but it was a dramatic demonstration of just how unstable and turbulent this star's outer layers really are, and it gave scientists a treasure trove of new data about the physical processes happening on a star nearing the end of its life. This event matters for our story tonight because it shows us something important. We are not blind to what is happening with Betelgeuse. Astronomers around the world monitor this star constantly, using ground-based observatories, space telescopes, and increasingly sophisticated models of stellar interiors. If Betelgeuse begins showing the true precursor signs of an imminent core collapse, there is a reasonable chance we will have some warning, even if that warning comes in the form of hours or days rather than years. And that brings us to the single most important piece of physics in this entire story. The one thing that would actually give humanity a heads up before the light of the explosion arrives. And it comes from a particle so strange, it barely interacts with anything at all. Neutrinos are subatomic particles produced in almost unimaginable quantities during a core collapse. When the iron core of a dying star collapses, the vast majority of the energy released, more than 99% of it, is carried away not as light, but as a flood of neutrinos escaping the collapsing core. Neutrinos interact so weakly with normal matter that they can pass through the entire body of the dying star, through the walls of your house, and through your own body without you ever noticing, billions of them every second. But when a star's core collapses, the sheer number of neutrinos produced is so extreme that even with their famously shy behavior, some of them will register in neutrino detectors here on Earth. Detectors buried deep underground or under the ice in Antarctica, specifically designed to catch these ghostly particles. Because neutrinos are barely slowed down by matter, they escape the dying star almost instantly, while the visible light from the explosion has to fight its way through the star's outer layers before it can escape, a process that takes hours. This means that if Betelgeuse goes supernova, neutrino detectors around the world could register a burst of neutrinos hours before the visible brightening of the star becomes obvious to the naked eye. Scientists actually experienced exactly this sequence of events in 1987, when a supernova appeared in a nearby galaxy called the Large Magellanic Cloud. Neutrino detectors recorded a burst of particles roughly 3 hours before astronomers visually detected the brightening of the star. It was the first time in history neutrino astronomy had been used to observe a supernova, and it confirmed decades of theoretical predictions about how these events unfold. If Betelgeuse explodes, we can expect a similar sequence, a global network of neutrino detectors quietly picking up a spike in particle activity, giving scientists a short but real warning before the visual show begins. So let's imagine it happens. Let's say tonight, right now, while you are watching this video, the core of Betelgeuse finally collapses. What actually happens next, and how does it unfold for us here on Earth? First, the neutrino burst races outward, essentially at the speed of light, since neutrinos travel extremely close to that cosmic speed limit. Detectors on Earth would register this burst within hours of the actual collapse, though remember, the actual collapse happened 640 years ago from our perspective. We are simply now receiving the signal. Scientists monitoring these detectors would immediately recognize the pattern and alert observatories worldwide, essentially screaming across every scientific network available that something enormous just happened in the direction of Orion. Then comes the wait, the tense hours where the scientific community knows something has occurred but the public sky has not changed yet. This is because the shockwave generated by the core collapse has to travel through the star's outer envelope, a journey that, for a star as large as Betelgeuse, could take several hours before it breaks through the surface and releases the visible flash of light known as shock breakout. Once that shockwave breaks the surface, the star's brightness begins to climb, and this is where things become genuinely spectacular for anyone standing outside looking up. Over the following days, Betelgeuse would brighten dramatically. Current estimates suggest the supernova could become bright enough to be easily visible during the daytime, rivaling or even surpassing the brightness of the full moon for a period of time, and remaining visible to the naked eye at night for several months, possibly over a year, before gradually fading back into darkness. Imagine walking outside on an ordinary afternoon and seeing a brilliant point of light burning in the daytime sky. Not the sun, not the moon, but a dying star 640 years in the past, finally making its grand and final appearance in human history. It would be the kind of event described in ancient astronomical records, the kind that once made emperors and priests believe the heavens were sending a message, except this time we would understand exactly what we are looking at. For those with telescopes and binoculars, the view would be even more remarkable. Orion, the hunter, one of the most recognizable constellations in the night sky, would look permanently altered. The shoulder star, the one generations of stargazers have used as a color reference point, because of its unmistakable orange-red hue, would suddenly become the brightest point in that entire section of sky, completely reshaping the visual balance of a constellation that has looked essentially the same for all of recorded human history. Cultures across the planet, from ancient Egyptian astronomers to indigenous sky watchers to modern-day hobbyists, have all looked up and seen Orion in roughly the same form. This event would be the first time in written human history that this particular pattern in the sky would visibly and permanently change. Now here is the part that answers the most pressing question people have when they hear about a nearby star exploding. Is it dangerous? Could a supernova this close actually hurt us? The answer, based on current science, is no, and the reason comes down to distance and the specific physics of what a supernova actually sends toward us. Researchers studying supernova safety zones have calculated what is sometimes called a kill distance, the range within which a supernova could pose a genuine threat to life on a planet, primarily through gamma-ray exposure and depletion of the ozone layer. Most estimates place this dangerous threshold somewhere between 25 and 50 light-years, depending on the type and orientation of the supernova. Betelgeuse sits at roughly 640 light-years away, more than 12 times farther than even the most cautious estimate of the danger zone. At that distance, the explosion would deliver a truly negligible amount of radiation to Earth, nowhere close to a level that would damage our atmosphere harm biological life, or pose any measurable risk to human health. There is also the question of gamma-ray bursts, an even more extreme and narrowly focused type of high-energy event, sometimes associated with the deaths of massive stars, particularly when a star's rotational axis happens to line up directly with Earth. However, gamma-ray bursts are believed to require very specific conditions, including extremely rapid rotation of the collapsing core, and current models of Betelgeuse do not suggest it is spinning anywhere near fast enough to produce this kind of directed beam. Even if it did, the geometry would have to align almost perfectly with Earth for us to be in the beam's path at all, and there is no scientific indication that this is the case for Betelgeuse. In short, this is a star death we get to watch as spectators, not one we need to fear as potential victims. To put this in perspective, let's talk about history, because humanity has actually witnessed supernovae before, and we survived them not just physically unharmed, but often without even realizing danger was never on the table. In the year 1054, Chinese astronomers, along with observers in the Middle East and possibly indigenous cultures in North America, recorded a brilliant new star appearing in the sky, bright enough to be seen during the daytime for weeks. That star was a supernova, and the remnant of that explosion is visible today as the Crab Nebula, a stunning cloud of gas and energy roughly 6,500 light-years away, considerably farther than Betelgeuse, yet still bright enough at the time to become one of the most famous celestial events in ancient astronomical records. In 1572, the astronomer Tycho Brahe observed another supernova, now known as Tycho's supernova, roughly 9,000 light-years away, an event so significant it helped begin dismantling the ancient belief that the heavens were fixed and unchanging. In 1604, Johannes Kepler documented another supernova, appropriately named Kepler's supernova, located about 20,000 light-years from Earth. Each of these events proved that supernovae, even ones visible to the naked eye and bright enough to rival planets or even outshine them, posed no direct threat to life on our planet. Betelgeuse, despite being significantly closer than any of these historical examples, still sits safely outside any meaningful danger zone. So if it is not dangerous, what would actually change for us, practically speaking? Beyond the visual spectacle, scientists expect a supernova this close would provide an unprecedented scientific opportunity. We have never observed a supernova this close with modern instruments, satellites, neutrino detectors, gravitational wave observatories, and global networks of telescopes that did not exist during any previous nearby stellar explosion in recorded history. Astronomers would be able to study the earliest moments of core collapse in extraordinary detail, potentially resolving long-standing questions about how exactly massive stars die, how elements are forged and scattered into space during these explosions, and how the remnant left behind evolves in the aftermath. And that remnant is its own fascinating chapter of the story. After the outer layers of Betelgeuse are blown away into space, what remains of the core will likely collapse into an ultra-dense object called a neutron star, an object so compact that a teaspoon of its material would weigh billions of tons. Essentially, the entire mass of a collapsed stellar core squeezed into a sphere roughly the size of a city. In some cases, if the remaining core is massive enough, it could continue collapsing further, past the neutron star stage entirely, into a black hole, an object so dense that not even light can escape its gravitational pull. Which of these two outcomes Betelgeuse would produce depends on the exact mass of the collapsing core, something astronomers are still refining estimates on. But either outcome would leave behind a permanent, if invisible, marker in the sky where a bright red supergiant once stood. The expanding shell of gas and dust blasted outward by the explosion, meanwhile, would begin its own slow transformation into a supernova remnant, a glowing nebula of stellar debris that would remain visible to telescopes for thousands of years, gradually expanding and cooling, eventually seeding the surrounding region of space with heavy elements forged inside Betelgeuse over millions of years. Elements like carbon, oxygen, silicon, iron, all created deep inside a dying star and blasted outward to eventually become part of new stars, new planets, and quite possibly, given enough time, new forms of life somewhere in the galaxy. This is, in fact, exactly how the elements in your own body were created. Every carbon atom, every trace of iron in your blood, every element heavier than hydrogen and helium was forged inside a star that eventually died, in many cases through exactly this kind of explosive supernova death, and scattered into space to eventually become part of the world we live in today. In a very real sense, we are made of the ashes of ancient stars that exploded long before our sun or Earth ever formed. Betelgeuse's eventual explosion, whenever it happens, will be a continuation of that same ancient cosmic cycle. It is worth pausing here to address a common misconception people bring up whenever this topic comes up online. Some assume that because Betelgeuse is a massive, unstable dying star, its explosion could somehow disrupt our solar system directly, damaging planetary orbits, altering the sun's behavior, or triggering some kind of chain reaction. None of this has any basis in real physics. Gravitational influence weakens dramatically with distance, and at 640 light-years away, Betelgeuse's gravitational effect on our solar system is utterly negligible, far too small to measurably influence planetary orbits, the sun's fusion processes, or anything else happening within our own cosmic neighborhood. The only things that will reach us from this explosion are light, across the entire electromagnetic spectrum, an early burst of neutrinos, and eventually, over an enormously long timescale measured in tens of thousands of years, the very outer edge of the expanding blast wave itself, though by the time it could theoretically reach our solar system, it would be so diffuse and weakened by that distance and time that it would pose no threat whatsoever. There is also a broader lesson in this story about how we as humans relate to events on truly cosmic timescales. We often want definitive answers, an exact date, a specific year, a countdown we can circle on a calendar, but the universe does not operate on human timescales, and stars like Betelgeuse exist within timeframes that stretch far beyond anything we experience in daily life. The most honest answer science can give us is that Betelgeuse will explode. It is a matter of when, not if, and that when could be tonight. It could be in 1,000 years, or it could be in 100,000 years, and from a cosmic perspective, all of those timeframes are essentially the same footnote in the life of a star that has already burned for millions of years. What makes this particular story so captivating is the strange intersection of certainty and mystery. We are certain Betelgeuse will die as a supernova. We are certain that explosion will be visible from Earth, dramatically altering one of humanity's most recognized constellations. We are certain it poses no danger to life on our planet. And yet, we remain uncertain about the single detail everyone wants to know most, exactly when it will happen. That uncertainty is not a failure of science. It is an honest reflection of just how vast cosmic timescales truly are compared to the brief span of a single human life, or even the entire span of recorded human history. So what should you actually do with this information? First, appreciate the sky a little differently the next time you find Orion overhead. That reddish shoulder star has already, quite possibly, finished its life. The star itself may no longer exist in the form we see it, and what we are looking at could simply be the last light it ever produced, still traveling toward us, still 640 years away from delivering its final message. Second, keep an eye on real scientific reporting rather than sensational headlines whenever Betelgeuse dims, brightens, or does anything unusual, because as we saw with the Great Dimming event, genuine scientific explanations are almost always more interesting and more accurate than social media speculation. And third, take a moment to sit with the scale of what we have just discussed. a star roughly the size of our entire inner solar system, nearing the end of a multi-million-year life, is going to die in one of the most violent and beautiful events the universe can produce. And when it happens, humans on Earth will get a front-row seat to a spectacle unlike anything witnessed in the era of modern astronomy, all without a single shred of real danger to our world. If tonight is the night, we will not know it immediately. Somewhere deep underground, in detectors built specifically to catch nearly invisible particles, a silent flood of neutrinos may already be arriving, the first quiet whisper of an ending that began 640 years ago. And in the hours or days that follow, the sky above Orion will begin to change, brightening into a spectacle that will be remembered, studied, and marveled at for generations to come. Until that day arrives, all we can do is watch, wait, and appreciate the extraordinary privilege of living in a universe where even the death of a star, hundreds of light years away, becomes one of the most beautiful and safe cosmic events we could ever witness. Thank you for spending this time exploring one of the most fascinating stories in modern astronomy. If you found this deep dive into Betelgeuse and the physics of supernovae valuable, consider subscribing for more explorations of the universe, and let us know in the comments what cosmic mystery you would like us to uncover next.